One, two, three. Okay, dear students, we are glad to see you here. And today we are very happy to present you Professor Tao Xin with a lecture about reinforcement learning and large language models. Let's welcome our professor.
Yeah, great. Yeah. Thanks for securing for the great introduction. So I'm very happy to be here to have this opportunity to share some recent progress of RL for large language models. So, but before I get into the content, so I'd like to conduct a quick survey. So how many of you are working on reinforcement learning or have worked on reinforcement learning? Okay, great. Okay, there are quite a few. Yeah, that's great. So yeah, actually, I have also worked on reinforcement learning, deep learning, NLP, but maybe in 10 years ago. So at that time, we know that reinforcement learning is very successful for game playing. So at that time, there are also some exploration research on RL for NLP. So, but at that time, yeah, you can publish a paper using RL for NLP. But in general, those RL does not really work. Like if you want to use it for real world applications or real world NLP applications. So that's why when I got to know that RL was used in ChatGPT or GPT-4 training, so that's really surprised me. So it's really a great progress. Okay, so yeah, maybe before the introduction, so usually I tend to speak very quickly. So, I'm not sure, maybe you are not very familiar with my accent. So if I speaking faster and faster, let me know so that I can slow down my voice. Okay. Yeah, so I'm from Zhongguancun Academy. So actually last month I was still with Microsoft Research Asia. So just this month I joined Zhongguancun Academy. So that's 2 weeks ago or 3 weeks ago. Okay. So yeah, this is one page because some of you are very familiar with RL. Maybe some others are not very familiar with RL. So here is a one-page introduction to RL. So generally speaking, RL is to handle this kind of sequential decision-making problems. So that means that you need to take a sequence of actions, and maybe you will get some reward during the process, or more often you will get some final reward. So basically speaking, you can see that there is an agent. It interacts with an environment like a game or some other system, or auto-driving car. At each time step, usually the environment have a state called ST. The agent will observe the state, it will receive an observation. Usually we use OT. So there are two kinds of settings. The one kind of setting is like that the environment is fully observable. So in this setting, so OT is equivalent to ST. But maybe in most practical settings, OT is different from ST. That means you may only observe some partial of the environment. So if we use MDP, a macro decision process, to formulate the problem, for the fully observable case, usually we call it MDP. It's just a normal MDP. But for those partially observable case, usually we call it a partially observable MDP or POMDP. And at each step after observe the state, the agent will take some action like AT, and it will receive some reward from the environment or from the system. The reward is usually indicated using RT or RT plus 1. So the index will depends on how do you count the time step. And then the environment will transit to the next state like as t+1. Okay, so on and so forth. The goal of the agent or of our algorithm is to find some policy to maximize the expected long-term payoff or reward. So it's called ER. So here we have some further notations. Usually we want to find a policy or optimize a policy. So here pi theta. So the input of the pi theta is a state, and it will an observation. It will map a state to action A to an action A. And we have so-called trajectory, like maybe from the first moment S0, A0, then S1, A1. But of course, you can also put the reward RT, like the immediate reward, into the trajectory. And for a single trajectory, maybe we can compute the return. Like if the process is finite, that means the process will terminate in finite steps. Then we can simply like sum all the immediate rewards. But if for some like infinite process, we may need to use some decay factor like gamma times R1 plus gamma square times gamma R2, so on and so forth. And for the value, so you can see that we usually define the value. Value is somehow the expected long-term reward of a policy. So here you can see we assume that this kind of a trajectory is generated by a policy pi. And we usually give a policy, we also define the action value of a policy. So action value is it takes a state and action pair as the input. That means start from this action, from this state S, take this action A, and for all the future steps, we will take actions using the policy pi. So what's the long-term expected reward we will get from this policy pi? Okay. So if you can see that, so here there is a value there's a ladder value function. Value function is only defined on state. That means start from this state, and for all future actions, I will using pi policy pi to take action. So what's the expected reward? So you can see the difference between value and action value is whether the current action is determined. So usually because given the current state S, you can choose a different set, or you can have a set of different actions. So usually we define the advantage. That means what's the advantage of an action at this state? Because at this state, you may choose different actions. Different action may lead to different long-term reward. So you can see somehow the V pi is the average over or the maybe not average, the expectation over different kind of actions at this state. And Q, so this action value is only focused on this state and action pair. Okay. So for advantage, it will be used like in the PPO or you use in LLM training. So this is one page introduction to RL. Yeah. So forgot to mention that if you have any questions, feel free to raise your hand so we can have this kind of interactive discussions. Okay. So here is a one-page introduction to LLMs. I checked the schedule or the agenda of this summer school. I believe you have heard multiple talks about LLM. So basically, there are like maybe two major steps in LLM training. The first step like pre-training. So you need to collect and process a large scale corpus, like maybe with 10 or even like tens of terabytes tokens. And usually we pre-train a base model, like with using maybe thousands or tens of thousands GPU, high-end GPUs. Usually we use the next token prediction. This is standard language modeling. So given the preceding tokens, predict the next token. Okay. So basically we want to like predict the probability of a whole sequence or sentence, but we will decompose it into the multiplication of multiple or each individual tokens. And after the pre-training, then we move to post-training. Currently, there may be two kinds of main setting for post-training. The first one is supervised fine-tuning. In pre-training, usually we call it unsupervised pre-training or self-supervised pre-training, because you can see that we use, like, for example, the web corpus. We don't really need a human to label the data. So it's usually like pre-training is conducted in a self-supervised manner or unsupervised manner. For post-training, especially for supervised fine-tuning, we need to fine-tune the model with human-labeled data, like a given query or given a user prompt. What should be the right answer, or what should be a good answer to that input? So here, for example, we use X to indicate the user input. We use Y to indicate the good output or the right answer from the model or the agent. So here, because the Y should be like annotated or labeled by human, or should be like maybe also can crawl from some web, but need to be checked or double confirmed by human. So that's why we create a supervised fine-tuning. And then the second setting for post-training is like for reinforcement learning. We are forced scaling supervision, because for reinforcement learning, usually we can leverage more lightweight supervision. So because for super fine-tuning, we need a human like to label data or to even to write some to a good answer, especially for those complicated input or question. It's very hard or very time consuming for user to write a good answer. Okay. So yeah, here is like yeah, great. Oh, so yeah, okay. But yeah, by scaling supervision, I mean that for reinforcement learning, it can leverage like a more weakenized supervision, so that it's easy to collect a large scale supervision than supervised fine tuning. Like for example, for super fine tuning, like I write a question like what's the best place to visit in Harbin? So you need to write like a long answer. But for reinforcement learning, I just using the model to generate like two answers and ask a human to rank which one is better. So the labeling efforts is much lightweight, so that we can collect more training data or more feedback signal through for reinforcement training. Yeah, yeah. So any other questions? Okay, yeah. So if no questions, so we'll move to the this is a 5-year journey of LLMs. So I won't count from the GPT-1 to GPT-4. Okay. So you know that like GPT-1 is first published in early 2018. So it's purely based on transformer decoder. So I believe you will know the transformer structure. So encoder decoder. GPT is focused on nice token prediction. It's just a transformer decoder. Almost at the same time, BERT from Google, GPT-1 is from OpenAI, and BERT from Google AI. So it's purely like a transformer encoder. It's bidirectional. For decoder, it's unidirectional, maybe like from left to right. For BERT, it's an encoder, so it's bidirectional. It's like a mask several tokens in a sequence, and you want to recover or predict the master tokens. And actually, at that time, BERT is much more popular than GPT. So even before GPT-3. GPT-2 was like proposed 1 year later in 2019. So it's the model size is much larger, so 10 times of GPT-1, and it should demonstrate this kind of very short transfer capabilities. And then GPT-3 was published in 2020, so it's a huge model, 100 times larger than GPT-2. So it demonstrates this kind of few short learning capabilities. That means you given several examples, and the model will know what you want to obtain. And then like in 2021, so Microsoft. Before that, Microsoft already invested in OpenAI in 2021. So I think maybe this should be the first large scale application, put a large language model into a product. Microsoft developed this so-called GitHub Copilot. It helps like millions of developers to simplify their work or to improve their productivity. And then the big news happened like in late maybe November for 2022. So it's the ChatGPT is it went to public and generate a huge noise, and it really like it's go beyond like NLP research, go beyond machine learning research. It's just like can help almost everyone in different kind of industries. And yeah, maybe then in March 2023, so GPT-4 came out. It's a huge thing. And someone like some previous colleagues in Microsoft, they even claim this is like an early version of AGI, artificial general intelligence. So actually, maybe just like in 2022 or a few years ago, so if you ask some senior experts in machine learning or in AI, you ask, when do you expect AGI will come to real? And maybe some like optimistic estimation time maybe take like 20 to 50 years. Some like maybe pessimistic estimation like it may take like 100 or 200 years. But it turns out that technology always advances much faster than we expected. But you know, after like this is GPT-4 came out in 2 years ago. Actually, we also observe like a huge advance in this domain, but I didn't really list them here. On one aspect that there also there much progress, but maybe it's not like as significant as like from like ChatGPT to GPT-4. And of course, you know that maybe many audience in the public are still waiting for the GPT-5. So it has like it took like for like maybe more than 1 year. And I also heard some reports, maybe rumor or maybe real news. Even include Sam Altman also claimed that GPT-5 like will come out maybe in a few weeks or maybe next week. Yeah, who knows? Okay, hopefully it will come out very soon. Okay. So yeah, here we show a very brief comparison between SFT, supervised fine tuning, and RL in LL in large language models. You know, before the post training, after you finish the pre-training for the next token prediction, you got the base model, but the base model can only focus, or it only focuses on language completion. That means you input something, it just complete the sequence. It doesn't not really answer your question or get your intent. For example, if you ask which is what's the highest mountain in the world, maybe it will continue like what's the longest river in the world. So it doesn't really answer the question. It's just try to complete your sequence. So from the grammar perspective, the answer is also correct, but maybe it's not what you need. So for secret fine tuning, it will focus on like this kind of input-output pairs. Actually, it acts as a format teacher. That means it will teach the model to respond to user's intent. So someone also concludes that for supervised fine tuning, it does not really introduce new capabilities to the pre-trained base model. It's just like try to teach the model to understand there may be different kinds of output. Which one or what's the intent of the user, so that the model can correctly answer user's input. For RL, it aims to align model with human preference, because somehow like this kind of ethical issues, or maybe you cannot output like toxic this kind of output. So so usually RL try to like give align the model with human value or with human preference. Now also it's for some in some cases RL can be like adapt to train foundation model to solve a specific task. Regarding the new capabilities, someone claims that RL does not really like introduce new capabilities to the pre-trained models. But someone also claims that it's indeed introduced new capabilities. So it's still unclear so far. Yeah. But maybe it also depends on how do you define new capability. Yeah. Oh, yeah. Yeah, actually, so I will show an example later. So basically, but I can tell you that, maybe you heard about DeepSeek R1. So that DeepSeek R1 is using a very simple reward. It does not really, in the training, fine-tuning training data, they don't really have this kinds of sort process or the COT, the chain of sort process. But it only provides yes or no answer to the final reward. But after the RL training, so somehow the DeepSeek RL1, it got to learn how to reason in the past, get the correct answer. Another example may be easy to understand is AlphaFold, AlphaGo or AlphaZero. This is for chess playing. So you know like that previously like chess play this agent they just learn from professionals, Go professionals. This kind of so usually they cannot like go beyond the top human professionals. But after the reinforcement learning, so because we know the final reward, we can evaluate the performance. So it like for the AlphaGo, it can learn or it can invent some new strategies that human professionals can never think about. They have never played this kind of strategy. So there's like somehow very surprising to human professionals. So that's maybe we can for this kind of new strategy or new capabilities. Yeah, just like if you have a well-defined reward, you will learn maybe invent or figure out some new ways to solve the problem. Yeah, so yeah, here is good. What's the difference between the supervised and the unsupervised? Oh yeah, okay, I see. So you mean the difference between supervised fine-tuning and the training, right?
No, unsupervised style transfer.
Or unsupervised
Style transfer.
style transfer. Oh, I see. Yeah, I see. I think yeah. First of all, they are two different things because you know, like for supervised tuning, usually we talk especially focus on like large language models. For large language models, that means the difference between like the supervised tuning and the pre-training is like supervised or unsupervised. But for unsupervised style transfer, usually there is no one-one mapping. So I'm not sure. Maybe you know for this kind of image, for the image style transfer, like you transfer like maybe the winter image to a summer image. So because in the training style, in the training process, there is no paired image. Like for example, this is the picture in the summer, maybe this university in summer, and this image of this university in winter. There is no kind of paired image. So that's why it's for the unsupervised style transfer. You know that this is a collection of winter images. This is a collection of summer images. But there is no one-one mapping between the image in this side and the image in that side. And so if you learn this kind of style transfer, that is for the like unsupervised style transfer. But here in supervised fine-tuning, we indeed have XY pair, and for this input, this is the desired output. So it's kind of supervised side, not really unsupervised side.
So in an event when we do not have a paired data sets, so supervised fine tuning is not going to be possible. Only what do you call it? If we want to fine tune a model, but then the data sets we have it's not. We don't have a paired data set to conduct that LLM fine tuning. So we have to revert back to unsupervised style transfer, right?
Sorry. So you mean for LLM and unsupervised style transfer?
Oh, assuming we want to fine tune an LLM to conduct to do some domain specific task.
I see.
So, but unfortunately, we do not have a paired data set to make that LLM to be a domain specific task. So, what's our best option?
Yeah, maybe I think maybe this kind of unsupervised, somehow like a style transfer. You know, the key of style transfer is like a distribution matching. So because there's no one-one mapping between the detailed samples, but I have like a set of this distribution, a set of another. We have two distributions. Of course, this is a distribution represented by a set of examples. So that means we focus on this kind of a distribution matching. For this kind of supervised fine-tuning, it's focused on this kind of sample matching. So if like we want to, for a general LLM, we want to adapt like for someone like for sports or for political news. So we have no labeled data or paired data. Then I think unsupervised step transfer may be a good approach. But it's hard to answer which is the best one. So maybe always we can or invent we can design some better approach.
Okay, so which one is apart from the unsupervised strand transfer? Is there any industry standard method to do that?
I'm not sure. Previously, like maybe 5 years ago, at that time, GAN, so generative adversarial network is very popular. At that time, seems GAN is very popular for this kind of unsupervised style transfer. Maybe nowadays, like diffusion models. So yeah, I don't think there is industry standard. Also, still depends on the problem, your problem setting, and also what kind of data you have, and also scale of the data you have.
Okay, thank you.
Yeah, thank you. Yeah, so, okay, so now let's move into the IL post-training. Okay. So, yeah, before I talk about IL fine-tuning or IL post-training for LLM, I first need to talk about this paper. It's this IL from human preference feedback. So this paper is published in 2017. Previously the deep reinforcement learning was popularized through deep mind in playing those games like Atari, this kind of video control games, or Go, this kind of board games. As for those games, you have very clear reward signal, like the scores displayed in the video screen, or the final whether you win or lose a goal. So this is you have well-defined reward signal. But in many practical applications, actually we do not have well-defined problem. Like if you want to control, or if you want to teach the robot to do something, like to clean the table, okay, so, or to clean the floor. Because the control, the degree of the robot is different from human. Your humans do not really how to send the signal to each sensor. This robot have many sensors, maybe 10 or 20 sensors. So how do you control those? It's like those joints. How to leverage those sensors? But human really can understand or can recognize the desired behavior. For example, this trajectory is better than that trajectory. So this is why we mentioned that through reinforcement learning, we can scale those kind of supervisions, because you do not really need to demonstrate the right actions or the right behaviors. You only need to label like which behavior is good, which behavior is bad. Those behavior can be generated by the agent or by the robot. So it allows agent to be taught by non-expert users. Even for non-expert users, they can label which one is better. Maybe non-expert user cannot, for example, like just for write a good article. The general user maybe not good at write a very great article, but the general user can understand which article is bad, which article is good. Basically, like the IR algorithm interact with the environment. It will generate like multiple trajectories, and the human will feedback which trajectory is better. We'll give some score to the trajectory, and then we will train a reward predictor. So here, like is the R. So usually we use the sigma. Or sigma is a function of the trajectory or of the state action pair, and then we given the two trajectories, sigma 1 and sigma 2, we can define the winning probability of sigma 1 over sigma 2. So like it's just like somehow like a sigmoid function, okay? So if you and so the loss is defined if human have some preference, like which one sigma 1 and sigma 2, which one is more preferred, mu1 and mu2 is the
1 to 3.
Yeah, sorry. Yeah, given the preference data, so we can using the methods presented in previous slides to train reward model. Then given this reward model, we can optimize policy. That means we sample a new prompt from the data set. We use the policy to generate output, and we use the reward model to calculate reward score for this output. And then we use this score to update the policy. So specifically here we use the PPO, so the proximal policy optimization method. This PPO method was also proposed by OpenAI. So here a bit more details for the PPO algorithm used in GPT. So first of all, this is pairwise preferences. So that means we want to train the reward model. So we want to the reward model is align well with human preferences. So if YW means the winner output, and YL is the loser of the output. So these two output, YW is better than 1L. So that we hope that the reward model will give a larger score to the winner one over the loser one. Okay. So you can see that this actually is somehow like a KL divergence. So defined by the log probability. So with this learned reward model, so R theta, the reward model, then to train the policy model, actually this has 3 loss items. Of course, the first one is reward generated from this XY pair. So X is the user input, Y is the model output. Well, of course, we want to maximize this reward. And the second one is that this is a KL constraint or KL divergence between the RL policy, or that means the updated policy, and the start policy, the supervised fine-tuning policy, because we do not want to the model over optimize to the reward model, because somehow the reward model may be not that perfect. Okay, so somehow it's also called in reinforcement learning community. If you overfit or over optimize to the reward model, it's called reward hacking. Another loss item is the pre-training gradient. So this is just like a lex token prediction loss, because it's observed that without this loss, somehow it will like forget some capabilities obtained in pre-training. So it will also introduce the pre-training loss in the RL training. Okay, so this is the overall training loss for the PPO or it in Isra GPT. So here we show the results of the Isra GPT. So it's
Okay, thank you very much. I have a question about reward modeling. At the previous slide, where you show only one reward modeling and mentioned that there is a problem with reward hacking. How do you think increasing the numbers of reward model, different numbers of reward model, can boost the abilities of the LLM?
Oh yeah, of course. I think if you like ancestral reward model, definitely you will like you can use the model and also risk of your hacking. Yeah. Yeah, of course, we can like assemble multiple reward models, but there is another risk is that this kind of reward model is really also huge, or also comparable with policy network. Like for example, maybe a model with 100 billion parameters. If you like want to assemble multiple reward models, the memory cost and also computing cost is huge. So and I will also talk about there are many researchers try to reduce the cost of reward model. Yeah. So, but in principle, indeed, you can like, yeah, indeed, in principle, you can reduce the risk of reward hacking if you assemble multiple reward models. But it will like lead to other potential issues. Yeah, so here we show the results like for the IL fine tuning. Of course, this is also based on the super fine tuned model. You can see the winning rate over the super fine tuned model, like with you can, of course, because this is all compared with SFT 175B models. So for this one, like because this one for this curve is supervised fine tuned SFT model, so it's compared with itself. So the winning rate is like should be half. So that's why this is the 0.5. Interestingly, you can see like for the PPO or IL boost models, even for model with only 1.3 billion parameters, that means only 1 or less than 1% of the parameters, it can achieve better performance or accuracy than the GPT-3 model without like the reinforcement fine tuning. So this demonstrates the power of reinforcement learning. And yeah, okay. Yeah. So we have talked about that IL, can somehow scaling the supervision because it's reduce the effort of human annotation, but it still need human annotation. So there is another approach called AI feedback. So this is like proposed by Anthropic. So you may know in addition to the GPT model from OpenAI, now this is another very popular model, the Cloud 1, 2, 3, 4, currently 4. So it's the cloud model comes from Anthropic. So this work is also come from Anthropic. So they propose like in AI, in human feedback. So given or given input, so it generate like multiple inputs, and we ask a human to rating which one is better. Give a reference, and then we train a reward model from human feedback, and then using this reward model to train the policy network, to train the language model. But here, like that, we instead of using human for rating or for ranking, we're using another LLM model. So it's somehow like we maybe this LLM model is not for generation. It's just to judge which model or which output is better. For example, XY1, XY2, which pair is better. So with this ranking, so we can train a reward model. So from this AI feedback, so we can using this AI feedback or the reward model to further improve the policy. So so the only difference is that how do you get the ranking or how do you get the parameter data from AI, another language model, or from a human. But here maybe the goodness or how good of this LLM model will like impact the future performance of your model, your algorithm. Because if this model is like perform very badly, then maybe these ratings are very preferences are very bad. So here, that's why in this paper, so the AI feedback, they show that, like for example, given the IR model, IRHF model, they generate some response, and they further ask the model to do some reflection, to try to self-criticize, itself, and try to make revisions so that get some better answer. And then with this model, they use another AI feedback model to generating and to get the model, and then to train the final so-called RL, CAI. So this C indicates the constitution AI model. Okay. So here is an example of AI feedback. Like this may be the original model output, SFT model. Human asks some questions, and the model will output. Because this question suppose the model should not answer, or should give some like other answers.
Could you please say more about constitutional AI model? Like, I think I missed it. So what it is, the constitutional AI model?
Oh yeah. So constitutional AI model, so it means it's just like it's give a name to AI feedback. So because it's like based on some other AI models, not based on human. So but I personally I do ask why they using this specific word for this like for their approach. Yeah, but maybe just try to be different with like human feedback. Yeah. Okay. Yeah. So here is the original input-output pair. Of course, suppose you should not tell human how to, or tell a user how to really hack into your neighbor's Wi-Fi. So then here we give some input to the LLM. So like say you need to understand whether your answer is harmful, is unethical, or whether dangerous or illegal. So the creator will the model will give some feedback and take this feedback into input, and then the language model will provide a better answer to user. So that means by doing so, better we can get a better input-output pairs for the model training. So this, because you can see this all those revision or the reflection, self-critical revision are all using AI models. It does not really involve human. So here it shows some model. Actually, for this kind of feedback, is meaning for this kind of reduce harmless or reduce harmful response. So where usually because your language model, we roughly speaking we can have two metrics. One is helpfulness. The other one is harmlessness. Helpfulness that means how useful or how actually you can answer user question. But for some question, you should not answer. So if you want to improve the helpfulness, sometimes you will increase the harmless because you will answer some like very dangerous questions. So it's supposed you should not answer. So here you can see of course there are some results like this one is called the including consider both the helpfulness and also the harmlessness in reward. So this is how the performance, and this one is only consider the helpful ILHF. So of course you can see if you only consider helpful, of course you can answer a user question more accurately. You get a higher score in terms of the helpfulness alone. But if you consider the harmlessness ranking, so also this model, so you have this curve, so is better in terms of helpfulness, but it's worse in terms of, because it will generate some maybe very dangerous or very harmful response. And but interesting, like for here, so this is what is proposed, or this kind of with COT, they can achieve a better trade, or even in terms of achieve very bad in terms of both of the helpfulness and also the harmlessness. Yeah, but I think currently most popular is still based on human feedback. So AI feedback is also very useful, but you need to combine it with human feedback to ensure. Because sometimes, garbage in, garbage out. So only using with using AI input, your performance will be upper bounded by the your reward model. Okay, so now we move into our reasoning. So actually, reasoning is a very hot topic recently, maybe since the end or the second half of last year. Here I want to first introduce the GPRO or GRPO algorithm. So it's called the group relative policy optimization. Yeah, this actually is try to improve the PPO algorithm. So because PPO actually has multiple models. You can see it has a policy model to optimize. You have another value model to optimize. As I have introduced in the one-page introduction to RL. So the advantage of this action maybe over other action at this state depend or is equal to the value of this state action pair minus the average value of this state. Okay, so you can see that to compute the advantage, then the model PBO need to multiple models. Of course, there is a reference model. This is for KL divergence. There's reward model. This is for reward commutation. This is for Q. Reward model corresponds to Q. And then there is another value model corresponds to this V. So you can see that we have at least two models to learn or to train. Usually the value model is also huge. So that means it's usually memory and the computation cost. And also, given that you have two large models to train, so it's tend to over optimize or to overfit those reward models, we may need to reward hacking. So that's how GRPO works. So actually, it remove this kind of the need for the value model. It's simply like for a single query or user prompt, it's generate or sample multiple outputs. And for multiple outputs, you can use a reward model to give a score for each output. And then give the multiple output, you can compute the average reward or average score for those outputs. And then the advantage is computed by, for example, the gap between this R1 over the average value. So just like the advantage over the average value. So you can say this system will become much larger, much simpler, simpler than PPO exam. Here it shows the results compared with like previous methods. Like this is for math reasoning, for math problem. Because usually for those math problems, it's very complicated. So you need a human to reason to get a correct answer. So here we can see that like the DeepSeek Math 7B is much better than similar size model, and even it can even perform similar to the GPT-4 API at that time. So this is in early 2024. GPRO, GRPO. This is a typo. So GRPO is I say on one hand, GRPO is a contributing factor for the great performance of DeepSeek Math. Another contributing factor is a high-quality math data set. It's the authors, they collect a high-quality math data set from the web with like about 100 or 120 billion tokens. And so actually in September last year, so you know that OpenAI released their model 01 model. So it's like maybe the first large-scale reasoning model. And it's first demonstrate the scaling law at a test time. Usually, we will know that for large language models, you training more time or you using more training data, more training GPUs, you will like get a better performance accuracy. In OpenAI 01, so it demonstrates that if you use more time for testing, like for COT, for chain of thought reasoning, so you can also get better performance. So this is demonstrated here, and there are more results like for the compared with GPT-4. This is for the math competition. This is for code competition, and also this is for PhD level science questions. Because for reasoning, usually we need to work on hard questions. For some simple questions, just like you may have heard this kind of system 1, system 2. System 1 focus on these simple questions. You may just like you can have a quick response. You can answer very well. But for reasoning, you need to think for a very long time so that you can get a good answer. What task is here? The math, code, and also the science question is usually science question here, the physics, chemistry, and the biology. Usually you need a domain knowledge or you need to reason to get a good answer. So O1 is like a very powerful in reasoning. But unfortunately, at that time, because OpenAI, they do not really release model, they even do not disclose the technical details. So usually we don't know how to reproduce or how to really enable reasoning capabilities in research community. Then here comes the DeepSeek R1. So this model really is very super powerful model. And here in this figure, it shows some results like on this kind of math, code, or science, also math, those kind of software engineering, software engineering benchmark their performance. So you can see its performance comparable with the OpenAI 01 model at the end of last year. So I think it's the first model that comparable, or first even open source model comparable to OpenAI 01 model on reasoning task. Then how did DeepSeek R1 achieve this progress? Actually, it's a start from the DeepSeek V3 base model. This base model is like no SFT and no supervised fine tuning, and it's just based on GRPO with some rule-based real signals I just mentioned. So that means given a math question, I simply detect whether the final answer is correct or not. is somehow like a 0-1 reward, binary reward. And for coding problems, I just check whether your code can pass my test cases. Another reward is format rewards. It want to enforce the model to put its thinking process, the reading process, into some special text like the beginning of think and end of think. So here you can see it's simply from the base. Of course, the base model is very, very powerful, but the base model is not good at reasoning. So simply based on the base model plus RL, it can already perform well for reasoning tasks. You can see here the comparison with OpenAI O1. It's like it's comparable with OpenAI O1 models. But of course, for some tasks, it's like still a bit worse. So it's this is just like without any supervised fine tuning or without really this kind of human labor data. So later in DeepSeek R1, so we'll use some human labor data.
Sorry, I have a question. You show in the results for the two types of tasks. The first task type is math, and second is code. And it seems, at least seems, that for code, the reasoning is not helping. Why do you think it is so? If you like switch a few slides back, there was like a graph where they show that reason is not helping, and as we can see here, it's not helping in for DeepSeek case. Why do you think it is so? But even commonly we consider that code and math are closed tasks.
Oh, I didn't get your point. You mean for coding is not help?
Yeah, it seems to be. Maybe it's like an illusion.
No, actually, let me tell you. So,
the previous one. What if you the previous slide? Previous. It's like from.
You mean
This one.
Yeah.
It seems to be that there is no help from reasoning here, at least.
Reasoning here. So let me check. You mean which? Mean for
the central one, the competition code, and we see that there is no like gain from reasoning.
Yeah, indeed again. So this is GPT-4o. So this is not a reasoning model. So I think it's a huge improvement for the reasoning model, right?
But for other models, we have a gain, as far as I understand.
I'm afraid I didn't get that point. So you can see for what those tasks, a reasoning model get a great.
Yeah. For math task or scientific questions task,
Yeah.
it has a gain. So when it's reasoning, it gains more quality. And for code, it seems to be not. Why do you think it is happening?
So what do you mean by a lot? I think the gain is significant here, right? From 11 to 60.
Yeah. But I mean this.
You mean this kind? Sorry.
Yeah. I mean this. Like, if we get, for example, O1 preview only, and we can see that for some tasks it has a specific gain from the reasoning, as far as I understand. The cap, the light cap for the graph. Yeah.
Sorry, I still didn't get it.
Like you see, scientific questions O1 preview only, and it has this additional web on top.
You mean the O1 preview compared with the O1?
O1 preview compared with itself, it has this.
You mean this one?
Yeah.
Oh, I see. I forgot. I forgot to mention. So this grid bar is somehow like is like using like ensemble results. So the gain like if you are using ensemble, whether you can get further improvement. So for some tasks like this one, I'm not sure whether it's show or didn't show this ensemble result. But for some questions like it's indeed like can generate a great result. I think for coding, one possible reason is like for coding we have huge training data like GitHub. You can collect huge for training data. But for the for math and for science, you don't really have that large scale training data. So that's why, because the training data is not large enough, so that you can maybe after ensemble you can get a better improvement. But for coding, you have already huge training data. So the ensemble of the model does not really need to further improvement. Yeah, sorry. Okay, so yeah, so we have talked about the DeepSeek R1 model, and yeah, so this it has demonstrated that IL empowers DeepSeek R1.0 to achieve robust reasoning capabilities even without the supervised fine-tuning data. But of course, supervised fine-tuning data can still help. So this I forgot to mention this kind of so-called aha moment. So this is also why I mentioned that this is so-called like maybe it's kind of new capabilities, because in the DeepSeek R1.0 training, it's just provide this kind of final reward like yes or no. The ground truth is just like a simple answer. There's no reasoning path. And but here, so you can see during the training for DeepSeek R1.0, is this kind of self-reflection. So you can see self-reflection, although advanced problem-solving capability is emerged from the training process through IL learning, but there's no training data in the IL training. So this kind of self-reflection. So that's someone argue that IL can indeed teach the model with new capability or can boost the model with new capabilities. You can see the example. Let's re-evaluate this step by step to identify this kind of self-reflection. This kind of data is not like include. There are no this kind of data in the training or the IL fine-tuning stage. Okay. So then from DeepSeek R1.0 to DeepSeek R1, there are some like several further enhancements. The first one is like it starts from supervised fine-tune. It's super fine-tune the base model with thousands of COT data. So in the R1.0, there's no this kind of COT or super fine-tuning data. And then after super fine-tuning, it's using the same the R1.0 like reinforcement learning plus some language consistency reward. Yeah, for this one, because it's that's not like if without the language consistency reward, it's try to mix different languages. For example, maybe the Russian and the Chinese, they mix together, so not very friendly to users, or Chinese and English mixed together. And then they further super fine-tune the IL trained model, and then do another round of IL for Word-selector. Word-selector means both the reasoning questions and also non-reasoning or the general input-output pairs. Okay, so this is so you can see actually it has two stages of super fine-tuning and also two stages of IL. Okay. So after this kind of training, so DeepSeek R1 probably very close, comparable to the OpenAI O1 model at the end of last year or early this year. In the DeepSeek R1 paper, it's discussed a lot about the technical details, but it does not discuss how should you collect or curate the IL data. So there is a paper like came out roughly at the same day or same week from another startup company, a language model LLM startup company in China. So it's discussed how to or several principles for the IL data curation. Like first, like you need to consider coverage, diversity of the data. Like you should cover diverse topics, including STEM, coding, general reasoning. And we should also balance the difficulty. You should have both simple and difficult questions. And also for those questions, you should be easy to evaluate the quality of the answer. Like for math, you can directly evaluate the question, or for coding, we know how to test the generated code. Okay, so the success of DeepSeek R1 so has like somehow incentivized a new or sub area for like reinforcement learning with verifiable rewards. So by verifiable rewards, that means we do not really need to use a neural based on neural network reward model. Don't need to train the reward model. We just use some like simple rules to define reward, like whether it is a exact answer for math, whether the generated code can pass the test case. So this topic become very popular, especially in the past several months. So here I will show several studies about there are many studies try to reproduce the DeepSeek R1 or try to improve DeepSeek R1. So this work try to understand whether like for example, I really incentivize reasoning capabilities beyond the base model. So beyond base, that means whether the answer already encoded in the base model, but because for base model it can generate many different kinds of answers. Maybe the right one cannot be generated with large probability. So for this work, it's found that it cannot study, for example, for same question, I can generate like 200 answers. Like for the base model, you can see that there are many answers. And for some paths, for some answer, it's also correct. But maybe with a very small probability. So that means for base model, if you use a base model to answer a math question, you can only generate the correct answer with a very, very low probability. But the correct answer can also be generated if you sample many times. The people find that for this kind of IL VR model, so with verified rule like DeepSeek R1, so it's somehow it can depress the probability of this kind of bad answers, but can promote the probability of those good answers. Okay, so it's showing in this case. But it also finds that for some cases, actually, for the base model, the good answer is included in its search path. But after reinforcement learning with verifiable reward, the good answer are somehow removed from the search path. So it's concluded that all the reasoning paths in IL VR model are already included in the base model, but because maybe with very low probability. So it shows that the average performance is like pass at one. So you can see the pass at one. If that means you only sample one example, it can indeed increase. So like with the GPR algorithm. So this is Qianwen. So Qianwen is a open source model also developed like by Alibaba. Okay. Or the training, if you sample more samples, indeed the for the Qianwen base model, the model can also improve the success rate for pass at k. For pass at 1, you can see the GPR can significantly improve the accuracy. But for large k, like for more than 200, the k is that means you sample a large number of answers. Actually, the GPR, this IL doesn't really help over the base model. So, so the conclusion in this paper is like that this IL VR method, they can improve the sampling efficiency. That means they can help to sample good answers with larger probability or make it more efficiently. But it does not really initiate a lower reasoning path or beyond the base models. So this is conclusion in this paper. And another interesting study, maybe not that accurate. This shows that even, for example, for IL VR training, you only need to have one training example. You don't really like have thousands or millions of training example. You just with one training example, for example, you just use this pi 1 or pi 1/3, just one training, one short training, you can already get a very good performance, even comparable with like thousands of mass training data set. So this is concurrent. And so somehow demonstrate whether I really need so much training data. Okay. So this these findings are very significant. But I will mention that this work was challenged by other researchers very soon. Yeah. And here is another study, like they try to understand because this kind of rule-based reward, it looks very simple. Why it can work? It works so well. So here is design some like a different reward signal. For example, like this correct answer, using correct answer. And it's also use some other like random reward. That means when you output some answer, I just random assign 0 or 1, whether it's correct or not. So you can say those reward signal like has zero information. It's a random reward. Or you can really somehow sometimes it can only give another method, like it's purposely assign an incorrect label. You purposely like flip the label. So and interestingly, you find that for the Qianwen, the more base models, for all those models, you can lead to significant improvements. I mean, even you give a random reward, you give an incorrect reward or the reverse reward, it can also improve the baseline model. Okay. So then But it seems the model, this kind of reward does not work for other models like Llama or OLMO, so it does not for this. So somehow they pose the question. So that's why really why ILVR really works. Okay. Here is another method that because this is even given that run maybe.
Yeah, thank you very much. Could you please could you please comment on the spurious rewards, especially incorrect reward or random reward? Why do you how do you think why it improves the quality of the model? And taking this into account, how we may rethink the training process of the LLMs?
Yeah, okay. So actually, this paper was changed because in principle, you think that the random reward or incorrect should not really help the training process. So I will talk it very soon. So you will see that because, or the answer is that maybe the baseline report number is incorrect. So for example, here you can see the baseline number is like only about 50. So but actually it should be like close to 80. So that if you input the correct baseline should be 80, then you compare with those real signals, you can see there will be no improvement.
So it means that the quality of the initial data, which these models were trained on, were pretty bad, so that even training with random reward significantly improves the scores. Yes. So the training data was very poor quality, such that even incorrect labels improve significantly. Yes.
No. So if you set the right baseline, so like the baseline model, if the right baseline should like the score should have like about more than 80. So for this case, you can see that the incorrect, if you give the incorrect label or random label, actually the performance will be worse than the baseline model. Yeah, because that means because the baseline score was underreported. So in the baseline, you underreport the baseline. So even you give a poor model, a poor signal, so it's kind of like improve the performance. Actually, it's not the case. Okay. Yeah. So here is another principle because somehow it's tried because the very simple reward can improve the performance, like the accuracy reward, the fellow accuracy reward, or the formatted reward. So this paper proposes that maybe IL can learn from its the self confidence. By confidence means that for this response, we have the probability of each token. So you can see that for this probability. For this response, some token with large probability, but for this response, seems the model are not so confident because for each token, the probability are very close to each other. So yeah, so this paper proves that maybe we can just use the model's underlying confidence. So that means somehow like when I have low confidence, then I will choose some action with, I think this one, I'm more confident about this option, then I will reinforce my confidence over this response. So somehow like this is just like a self reinforcement or self boostment. So basically it will compute the entropy, like for each position you have the token probability over each token. So you will compute the you will compute the probability or the entropy of those tokens. And if we know that larger entropy means larger uncertainty, so it will try to reward those response or action with smaller uncertainty. So by doing so, we don't really need this kind of external reward. Yeah.
The paper on the previous slide that did the
you,
research of the previous slide.
you mean this one?
No, the next one when the confidence improves.
Yeah, there is a paper about you can, I think you can just search this.
Okay, just the number.
Yeah, you can search the okay. Actually, there are, at the same time, maybe just in 1 or 2 months, there are maybe 3 or 4 papers with similar idea about this idea. I think maybe, okay, yeah, okay, yeah, very interesting for this paper. For example, in the paper version 1 is posted to archive. It reports that doing so, they can need to like significant improvement. You can see the improvement is huge. But someone point out that there are some evaluation problems with their baseline. So after they refine the baseline, so you can see the improvement is very marginal or almost no improvement. So this is a latest version V4. So that's why I see there potentially some pitfalls for this kind of research in RL and LLM. We should be very careful about the evaluation. Now this another like a method is also like try to without external reward, just also using the cell for see the internal reward or internal state. If it can output some response or action with large probability, it will further reinforce this probability of the action. Somehow like in the graph or in the sort of like the rich get richer. Here the larger probability actions will get even larger probability. The actions with small probabilities will get an even smaller probability. So this is self-reinforcement. It's just use the internal reward signal. Okay. So here we mentioned the potential pitfall because just like in past 2 or 3 months, there are many papers study how to define reward signal. For example, paper one even random reward or incorrect reward can lead to improvement. But some research find that for those study, actually their reported gain like is huge. But if you use in the right setting for the baseline evaluation, you can see this kind of improvement actually is that there is no, the improvement is very marginal or somehow maybe just a noisy, or just some noise. And also for some results, actually this report some gain. If you set the right baseline, actually there is even no improvement. Actually the performance may be even dropped. So that's why to claim that or there's some observations and suggestions. So sometimes the baseline method, like for that means without IR methods are significantly unreported. So this may be also related to the ethical issue in research. So for example, if you want to highlight your algorithm or our algorithm is very good, you may underreport baseline methods. And also, you find that for some proposed methods, that means after their proposed post-IL training, their performance or actually is still worse than the baseline methods. So there are some suggestions for this kind of, if you want to study IL. I think it's in general, not only for IL or for IM. So you like you should use the recommended. If you compare with some baseline, you should follow the recommended setting for those baseline methods. For example, how to use the prompt, the format setting for language models, using right hyperparameters like sampling temperature, max sequence length. Usually for reasoning, you need to output a long sequence. So if the max sequence length is very small, then the performance or accuracy will drop significantly. Also, we should use a large benchmarks. Otherwise, a very small benchmark, the performance may be like a very random. With large variance, and also you should test over different baseline methods or base models. If you find some very interesting or even somehow abnormal or surprising results, you should like release data or model for like external evaluation or cross validation. And also, most importantly, do not rush into publishing paper. I think for those papers, like they may publish like in 1 month. So maybe they are afraid that their results, others will have very similar ideas. If you are not the first one, then your research will like do not have much value if you have some very similar idea. But again, we need to be very careful about really our research quality. Yeah, okay. So maybe the last topic I will discuss is IL pre-training. Maybe we will talk about how IL can help post-training. So this is that one. We know that like I'm not sure, maybe you know the left figure. So I think Ian Loper has used this image for many times. So for IL, it's like just like a cherry on top of the cake. For the main part of the cake, it's just like a next token prediction. It's for language modeling. And for reinforcement pre-training, so we want to ensure the or maximize the utilization of all the unsupervised data. So it's called like next token reading, not a next token prediction, but next token reading. So you can see here, for example, this is our corpus. General standard next token prediction, we just given the previous tokens, we just predict next token. But for next reasoning, we have to play the next token. We think about to determine the next token, we need to think about. That means for each token prediction, we have reasoning paths. So doing so, we can avoid that. We just simply memorize the training data. Instead, we want to ensure that we can really understand why the next token is the size, but not others. So this, I think the basic idea is very simple. For the given the LLM, we can generate multiple reasoning paths, and for each reasoning path, we have a word, we have the predictor token, and then we can check which one is correct. This is also in unsupervised manner. Okay, so this is called pre-training, and based on this, we can fine tune or we can find something like fine tuning, but it's in pre-training because this is using unlabeled data to fine tune the base model. Depending, you can see that compare with those base models because it's a word pre-training. For base model, especially for those very challenging or difficult tokens, you can see the accuracy improves significantly. But for easy ones, you can the base models can already perform very well, so there may be not great improvement. So yeah, they also verify the scaling law, like if we increase the computation budget, and the next token prediction accuracy will improve significantly, and especially for the I think here is a bit. I think the overall score is that for hard ones is still very harder than easy ones, but they both improve over the with respect to the increase of the computer budget. So I put this in a
Yeah, thank you. Could you please comment at which stage the next token reasoning is performing? In the inference of LLMs or during their training?
We are performing the reasoning during training. That means for each next token prediction, I need to reasoning multiple paths and check which one is correct, and giving this reward signal further to improve the training the model.
But how undertrained LLM can reason?
Yeah. So because it's here you can figure it's based on actually it's based on a pre-trained language model. So this language model can already do some reasoning, basic reasoning. Yeah. You just need to give it a special token, like you can see that that's fine, or that can be you give some prompt, then it can do some reasoning. Yeah. Maybe not that good, but it have certain reasoning capabilities.
I also have a question about next token reasoning, and my question is: will the LLM learn something readable by human between these think tokens, or it will be something not readable, maybe?
Sorry, I think that's very clear.
Between think tokens, the LLM can produce something, yeah? But we don't have a loss on it, as I understood. And the question is, will the LLM learn something interpretable and readable by humans? Or maybe it will be some mess of tokens?
Yeah, I'm sure whether I correctly get the question. So basically here, because for human, for human, we read something. Really, human have some reasoning path, which next word I should use, I should choose. So there's some maybe implicit reasoning in human mind. So I think for this work, they try to simulate this kind of reasoning path, and especially they want to mainly focus on those difficult tokens, because for difficult tokens, you need to think about which token should use. But for very easy ones, you don't really need to think about that. Just like system 1 thinking and system 2 thinking. For system 1 thinking, it's like instant feedback. You know the next way. You don't need to think about that. But for some very challenging tokens, you need to think about feedback. Like this, because this example, like the electronic force grows with charge. This is related to some physics. So we need to learn how what's the rationale between the next token. So you need to do some reasoning here. But I mean, maybe I didn't get answer.
Yes, but if we compare with human mind, like we have an input, we have a think process and the output. And think process not always in the natural language tokens, like it maybe can be something visual or something else. And the question was, will the LLM learn something like that, or will be there only like natural language tokens, like readable by humans in this think process here?
As far as I understand your question, the question is why the LLM is actually producing some readable thought about the token. So as far as I understand, it is producing because it's the only thing it can do, it's just producing text. So it should be text because it's the only thing it can.
But it can be something not structural, like answers.
I think it's not, because the LLM is actually seeing a lot of text and it only knows how to do text and nothing more. And this is the idea. And actually, I have my own question, if you allow me. As far as I understand this paper, they actually do not the every token reasoning. They reason only on the few tokens which have high perplexity. So this is because, as far as I understand, of really huge computation needed. So how do you think, how can we reduce this computation for RL pre-training?
Yeah, that's indeed a great question. So that's here I mentioned that it's only applied to difficult tokens because first of all, for the cost, for the reason it's very huge. It's like it's a very computation costly. And the other reason is that for some simple tokens, you don't really need to reason about that. Or the previous we talk about for some like a reasoning question like math, coding, or science. For other general questions, you don't really need to do reasoning. So that's by nature, for some tokens, we don't need to do reasoning. And but indeed, we need to think how to reduce the complexity of the reasoning. So that's why actually they do not really pre-train from scratch, like just like the GPT-3 or GPT-1 to just from scratch. They use some like pre-train only for this paper. If you check the paper details, they just do some pre-training, so-called pre-training on some math data set, a small math data set. Math is really more challenging. So it's just focus on math data set. And they also leverage like a pre-train level. They just somehow they should be continued pre-training. They use just like the token prediction to do a round of pre-training. And then based on this pre-training language model and do another round for maybe small round of like the token reasoning only for those challenge tokens. Yeah. Yeah, I think this should be the last slide. So far, we have discussed about the IL4 language models, great success, many exams, but also maybe also many pitfalls, and scaling, of course. Here I mentioned that how we get a better reward, even for the reinforcement pre-training. So the last work is also try to get more real data, because if we can do reasoning for these different tokens, we can almost any very, very large scale data from the web canvas. But of course, we need to consider more efficient, as I mentioned, we need to further reduce the complexity. I'm not sure, maybe nowadays they are so-called low precision or bitwise pre-training, or like a 1 bit or 2 bit. So this can maybe further improve the efficiency, and also this kind of MOE mix for expert. It can also, because the activation parameter for each token is very small, so can also improve the efficiency. But of course, in this talk, we didn't cover many other aspects like a visual language model or even the embodied AI robotics. Yeah, so I think still can be combined. This naturally can be combined with reinforcement learning. Yeah, thank you. So, any further questions? Yeah, thank you.
Okay, thank you. So in your lectures, I think you introduced GRPO as an evolution to PPO, right? I think during your lectures, you introduced GRPO.
GRPO, yeah.
Yeah, as an evolution from PPO, right?
Yes, yeah.
So if in my case, if for example, hypothetically speaking, if I'm working on a project to simplify a complex statements to make it more readable and understandable. So which this task requires a significant style change. So meaning the model must learn a policy that is quite different from its original state, right? So which also the PPO use KL divergence penalty to control this. It's use KL divergence to control this what do you call it, deviation. So my question is within the GPRO framework, what's the recommended approach for managing this trade-off?
What's the recommended practice for what?
For managing this trade-off, because the model must learn what do you call it to it's a text. It's a text simplification model.
Text classification, yeah.
So the model. So the model must learn to what do you call it to output a text different from what the output. It will deviate from its original knowledge.
Sorry, still, you mean that for text classification, the
Yes.
output is different from orange?
Yeah. Yes. So it has to change the style of the input, right?
Yes.
Because it has to simplify the text.
Yes.
Yeah.
Then what's your question?
So what's the threat of in model the deviation of the model?
Oh, I got it. So you mean the super fine tuning and the reinforcement learning model because the output are different.
Yes.
You mean that's a great question. So I think that depends on how do you represent your output. For example, for text classification, if you just you just using the text labels, like for example, this is dog, this is cat. It's just 2 words, right?
Yes.
But for the 2 words, you can still have probabilities.
Yes.
So for probabilities, you can still compute. You just can treat it as the 2 tokens with probabilities. But maybe you only focus on these 2 words, so that you can compare for the SFT model. What's the probability distribution over these 2 tokens, and the RL policy is a probability distribution also over these 2 tokens. So it's kind of 2-dimensional distribution, probability distribution. You can still compute the KL divergence.
Okay. Yeah. Thank you.
But you can have different kinds of definition. You can simply treat it as there are like a small or small size vocabulary. You can still compute the the KL divergence.
Okay. Thank you.
Yeah. Okay. Yes. Okay. Yeah. Thank you. So. Yeah, so hope you enjoy maybe the last 2 days here. Yeah, thank you.